Welcome, everyone. I know that you're joining. Thank you for being with us today at this webinar. My name is Rocio Garcia. I work at Sustainable Innovations, and I'm also the communication manager for the Fastest project. I will give a couple of guidelines for this webinar before we start. This webinar is being recorded, and we will give the edited version, I think, this week, also with the presentation slides and the contact of the 4 projects. If you want to make a question, we will have at the end 15 up to 20 minutes slot for this. You can either write them in the chat. You have this option on the Zoom, and there is another option. It's a box of Q&A. So either both of them, just please write at the name of the project and then the question. So it's easier to define all the questions at the end, and we'll address them at the end of the session. And as I was saying at the beginning, you will receive an email with the recorded video, the YouTube link, and also the content of the project. This is the agenda for today. After this guideline, I will give the floor to Bruno Rodriguez. He will explain the TwinBATT cluster, and he's also the project coordinator of the FAST project. And then we will go on with DigiBatt, Fastest again, THOR, AccCellBaT, and as I was saying, the Q&A and closing remarks. So thank you for being here. I think I will not take that much time, and I welcome Bruno. Hi, Bruno.
Hello, good morning. Good morning to you all. And thank you, like Rocio said, thank you for attending our webinar, our TwinBATT cluster webinar. To present myself, I'm Bruno Rodrigues. I'm project manager at Avesta, and I'm also the project coordinator for the Fastest project. I will share with you, let me just, so to this, okay. This is a very short introduction to why we are here today, and that is we are 4 projects that have been granted under the same call, that it was the topic, the Horizon CL 5222 D20107, and that our common baseline, it's about digitalization of battery testing. This is our main ground for all of these 4 projects. We are developing several approaches. You will see that we are very similar, but in somehow we are also different in the way that we are tackling this topic. And this cluster we are a newborn cluster, and we felt the need to start sharing between these 4 projects our insights and to keep this forward during the next the next periods until the projects end. And today it will serve also for you. The cluster, it's a newborn, like I'm saying, and this will be like a quick introduction to what these 4 projects are doing and how we are facing the topic. We will try to have more webinars until the end with more insights about the projects, with more results to be shared. And also we will be available, like Rocio said, in the end to tackle potential questions that may arise during the presentation, but also feel free to come back to us during the next period of time and to put questions, to put some doubts. We will be happy to answer all of them. And now, to keep with our agenda, I think, Rocio, we will pass the floor to Francesca and to DigiBatt
Yes.
project.
Thank you, Bruno.
Well,
Welcome,
thank you.
Francesca.
Hi, good morning. You can see me now?
Yes.
And here, and now you can see my presentation. Great. Yes, good morning, everybody. My name is Francesca Watson. I am a researcher in SINTEF Digital, which is based in Oslo, and I am also the project coordinator of the Horizon Europe DigiBatt project. It's a 3-year project which started in 2024, January, and will run until the end of 2026. the consortium that we have at the minute is made up of 8 partners. So we have SINTEF and Corvus in Norway, SINTEF being a research institute and Corvus working with maritime batteries in this project. And then we have Oxford in the UK and VUB in Brussels. And then we have FZJ Forschungszentrum Jülich and DLR in Germany, and then AVL and Virtual Vehicle in Austria. Yeah, so the DigiBatt project is, as I said, a 3-year Horizon Europe project. And the idea of the project, and in fact, all the projects in the cluster, is to look at digitalization of battery testing. And what we want to do is try and combine existing battery testing methods with state-of-the-art digital techniques so that we can make them faster and cheaper and more accurate. And the ultimate goal is, in fact, to allow us to extract more value from fewer battery tests so it can be more efficient. In terms of KPIs, we're targeting a 30% reduction in time and 20% reduction in the cost of battery development. Right, so when we're talking about testing and parameterization of batteries, we're talking about a few things. So the first thing can be physical testing. And so what I mean by this is if we have a lot of cells in the lab and we cycle them, and we can look at the discharge and charge profiles and see how they perform over time and over many cycles. So this is one of the types of testing that we are looking at in the project. Another type of testing could be destructive testing. So here we may be cycling batteries and inducing thermal runaway, or in fact looking at taking the batteries apart and doing some microstructural characterizations after they've been cycled to see how they have degraded over time, and looking in very great detail at the inside of the batteries. And then we might also talk about virtual testing or simulation, where we can run a simulation of a battery using the parameters that we want. So in this project, we're trying to combine all these 3 methods in a sort of efficient way that can help us speed up the whole process. Okay, so these are some of the problems we're trying to address with battery testing in general. So first, at the minute, we have a lot of people doing testing, a lot of people collecting different types of data in different ways, but we struggle to communicate with each other among what the data is actually telling us and how it was created, which means that even if data exists that might be useful for us, it's quite difficult to reuse that data in the future. So the test data that we have and the processes that we have are quite fragmented. Another issue is that testing is very time consuming. So it can take a long time to test a battery until it fails. And especially if we're looking for life cycle and safety data of new batteries, this can take a very long time. It doesn't mean we don't want to do it, but we want to do it as efficiently as possible. So we don't want to spend a lot of time doing a lot of long tests if they're not needed. And finally, battery testing can be expensive. We're running many different types of tests. And if we're not careful about it, we might also be running tests that are not actually going to tell us much more useful information. As well as the fact that if we're doing destructive testing or just cycling in general, the cells that we're testing are going to be destroyed at the end. So we need to be careful about how we do it in order to save time and money. So the way we want to look at this in DigiBatt is looking at standardizing, automating, and accelerating the testing procedure. So the first part, standardizing data formats, will help us address the problem with fragmented data. So if we can find a standard data format that we can keep our data in, and then we can pass it around between different actors, that will cut down on some of the bottlenecks to do with translating data into different formats and sharing data. The other thing we want to look at is automatic triggering of virtual and physical tests. So we can take out some of, but not all, of the sort of human bottlenecks and the things that slow us down if we can do this automatically and save some time. And then we also want to look at improving our testing methods. So increasing the efficiency of the virtual testing methods, and also being able to intelligently choose which experiments that we want to run the physical testing, which will save us time and money. The result of the DigiBatt project will be a toolbox of open source tools. So one of the key things that we're doing in our project is basing a lot of our work on open source software that we have already. So the idea is that if we make things open source, then everybody in the battery community can use the tools and adapt them to their purposes, and we can achieve wider reach that way. So the four main things we're looking at are having interoperable data models, and I'll talk a bit about that later. Also a digital twin infrastructure to bring a lot of the tools together. Strategies for intelligent design of experiments, and also a lot of this webinar will be talking about system cell level tools, because that's what we've been looking at so far, but we will also extending the work to system level tools as well. So we're looking at whole systems with batteries in. But I won't talk about that so much today, because we haven't quite got so far in the project yet. So in terms of standardizing data, so imagine that you are a battery scientist and you have a lab and you have a lot of cells, and then you want to cycle these cells, and you've been cycling them many cycles, and you've been recording the charge and discharge profiles. But you might not be able to tell everything you want to know from this data. So in order to find out some other parameters, you may want to run a simulation. So in that case, then you might give your data and your simulation, your cycling setup to your friend who works in the simulation lab and who simulates battery cells. But what you will find actually is that it's quite hard to communicate some of the parameters that you have to the people running the simulations. And even if you're the same person running the experiments and running the simulations, some of the parameters that you need to put into a simulation are not necessarily the same as the parameters that you might know from running the experiments. And it can actually be quite a difficult situation to be in. You may have a parameter that has the same name as something else, but it might not be actually the same thing, or it might have been collected in a different way. And so there's sort of a mismatch in understanding between different parts of this chain. And then also, if you want to look at finding out, telling the machine what to do when you're running an experiment, this might be even more complicated. If you have several machines that have different input formats and you want to run the same test on different machines, this might be very difficult to do. And also, if you're running a simulation and you want to use different simulation tools, they might have different input formats, and everything gets quite confusing. So what we like to do in DigiBatt is to look for a common language that is readable by humans and machines. And we're solving this by developing ontologies. So an ontology is basically a fancy word for a way to describe parameters. So a list of parameters and their description. And there exist larger ontologies, and as part of that, we are building specific ontologies to deal with battery testing parameters that we might want to know, and battery geometry parameters. So this diagram on the right is an excerpt from one of our deliverables where we have defined the battery cell geometries and the ontology. And you can see it's not quite so simple as just saying sort of the height and the diameter of a cell. We actually need to have a lot more parameters detailing very small, very different measurements. So if you want to read more about this, you can have a look at the deliverable linked in the top right of this slide. And also you can have a look at the repo where the ontologies live. Yeah, so once we have an ontology, this basically we use to JSON linked data format to describe it. So on the left here, you see the description of a coin cell, CR2032 cell. And you can see that it has different properties, and the different properties have different values, and then we have units for different values. And if you were to write this out by hand, it would be quite painful and take a little bit of time and quite a lot of room for error here. So the other thing that we're doing in DigiBatt is developing tools to help people write data in the ontology format using the ontologies. So we have a tool here called Cold, which is a Python package, which you can use to create the JSON LD data models. And you can see you just need a little bit of code, and then you can write your JSON LD file. And you can also read about this in the deliverable linked here. Right, so once we have an ontology, then what can we do with it? So one of the things that we can do is we can look at data that we have collected already, and we can turn it into the correct data format and write the JSON linked data file using the correct terms. And this is also something we have a package for. It's not open yet, but you can also read about it, and it will be open soon. And that allows us to look through data files on a computer or that already exist, and then see what the data is and try to convert it into the ontology. But then once we've done that, we can use the ontology as sort of general language to convert between different formats. So if, for instance, we have a test cycle description that's written in a certain way, and we are creating tools that allow us to run that on a certain testing machine. But we can also convert that test format and test specification into a simulation input and run exactly the same test, but using the simulator. So this is one way that we can reduce the chance of error, make things more accurate, and cut down on bottlenecks. So the other things we're looking at are accelerating battery testing. So one way to do this is to look at improved numerical simulation tools. So if we're doing simulations, we can make the simulators run faster and be more accurate. And in DigiBatt, we are basing a lot of our work on existing open source simulation tools that we have, such as PyBAM and PyBop, and also BATMO, which is used for cell simulation. And in this project, we're trying to extend these to improve the optimization and parameterization methodologies. And we're also looking at making them run more efficiently. So if you're interested in that, I won't talk about it now. This is not enough time, but if you're interested in finding out what we're doing with that, we also have a deliverable here, and there are several papers we can read as well. Another thing we can do to improve our numerical simulation, our virtual testing tools, are looking at data-driven methods. So using AI or other machine learning models to identify patterns in data that we have, trying to predict safety and lifetime characteristics, and see if we can find any indication of failure modes based on previous running data. And also, we're trying to look at how we can find which cases at a system level can be most important for predicting failure. So which cases are most important to test at a system level, use cases, in order to predict failure modes in systems. So there's also not much written here today about that, but we will be working on that in the future. And finally, we're also looking at ways to do design of experiments. So if you have something that you want to know, you have a certain amount of data about yourself, but you want to know something else specifically, we are looking at developing automatic ways to figure out what sort of tests you really should run to get the most information the quickest. And then with the standardized tools, we can automatically trigger the tests that we need. So to bring it all together, we will develop a digital twin framework, which has different parts that can do all these things here. So collecting data, deciding which tests to run, triggering the tests, and updating results. So these parts are not there yet, but the framework is beginning to take shape, and we have also information on that available. Yeah, so that was basically what I was going to say. If you want to have a look at any of our software, you can go to our website, and this is all open source software, so you can click on the links there and find the repos and see what we've been up to. And I would say that this is software that existed before the DigiBatt project, but we're building on it in the project as well. If you want to find out more about the project in general, you can have a look at our website. We also have a Zenodo community with software and deliverables loaded there, and a LinkedIn page as well. And finally, I'd just like to say we will be having a symposium in Oslo in June, where we will have several speakers, both from the DigiBatt project and the Intelligent project, which is another project we have, and also from industry. And they will go into a lot more detail about many different aspects of digital battery technologies. So if you would like to attend, we'd love to see you there. There's a link here. And also in conjunction with that, we will be having a workshop introducing people to the BATMO simulation software. Yeah, so I just wanted to mention that. Well, thank you very much for listening.
Thank you, Francesca. I think we can share both workshop links on the chat as well. Thank you. So now we'll move on with Bruno again for the fastest project.
Hello again. Let me share my presentation. Okay. So I will not enter in a lot of detail with fastest. I will explain the overview of the project and how we are tackling all this digitalization of testing for battery development. And what is the main goal of fastest, and why it is a very interesting project. We all know, and similar to what DigiBatt presented, we are and all the economics, all the things in the world, we are trying to rush how we put the battery development out and how we can improve and to put it in a fastest way, like it's the name of our project. And in this way, we are trying to develop a fast tracking testing platform that will be able to combine multi-scale physics, virtual and physical testing. This will try to speed up the battery system R&D and to try to present safer and long-lasting designs. We are tackling this in several way approach, and you will understand a little bit further on how we are tackling. We are doing all these multi-physical and the virtual testing, but also with a strong focus on safety. Safety is also a thing that we are trying to digitalize. It's not easy. It's been a tough challenge to try to overcome that, because it's nothing that you can quickly virtualize and do a simulation and we have it done. But it's an interesting point of also our project and how we are tackling about that. We are using several approaches on the virtual models and on the models itself, from the physical models to other ones. But let me go a little bit further. What are our main goals and main objectives with this project? It's to develop and test a fast tracking hybrid testing platform, lay down the pathway for results exploitation and dissemination, to develop and validate physics-based and data-driven models for simulating and substituting critical physical characterization experiments, then to set up a digital twin information management architecture, and in the end to stock take and propose efficient DOE strategies. These are our 5 main goals. It's not what we are the main objectives. These are the goals that we are trying to push forward with fastest. And for you to have an idea, this is how we are tackling and how our project is composed. We are defining DOE and our boundary conditions. We are using 3 use cases. We are going to use, or we are using automotive, heavy-duty vehicles, and home energy storage. These are our baselines to understand where we need to go, what we need to develop, and how we are tackling this. We are going from cell to pack level. So we are starting from cell, we are evolving then to understand how this impacts in module level, and we are aiming in the end to have, in a more simplified way, a pack level definition for our use cases. Inside our use cases, once they are defined and they are defined, we are doing cycling to understand the battery aging and performance modeling. We are feeding all the cycling data that we have to physical-based models. And then in the physical-based models, we are also using data-driven. We are also using modular data-driven, and also a PIN model that it will also, all of them will be used to feed our digital twin, and also to feed what's in the end that it's our LIMS, our library interface manager system, that will combine all of these. Together with this advanced battery aging, it's feeding our battery safety and reliability AI-powered toolchain. What we are trying to do is to use high-fidelity models that are being developed in a previous work package. And then we are also going to do some physical testing in the safety. We are going to do overcharge, over discharge, extreme temperatures, and also in the 3 layers that we are talking, from cell to pack level. In pack level, a little bit more, once again, more simplified, and also using some assumptions from what we are observing in the module level. And all of this will be compiled in the end in our digital twin. Our digital twin will be able to process what we are doing using the DOE, what the user is going to ask, using, once again, a work that it's also available to consult about ontology and to understand what are the main goals for the battery development. And in the end, it will give the user what are the right parameters, what are the right information, what they are looking for their cell, for their module, or for their pack level design that they want to do. What are we trying to aim with Fastest? We are trying to reduce in the digital twin part 20% less of operating time between simulations, runtime, and how things are improving. This is also connected with the 50 milliseconds faster computational time that we are trying to push forward with a lot of information, with a lot of data. So it's very easy for and also together using reducer order models to try to improve this time and to give as fast as possible the results. We are also aiming for the safety, reliability, and performance of this virtualization ratio. And we are aiming for 3 demonstrators, like I already told: automotive, heavy duty, and home energy storage. These are the big impact that we want to create with Fastest. We are a lot of great partners that come together to put this running, and we have from university, from academia, to automotive to automation, to battery pack and to pack producers, to RTOs, and I think all together we create a great consortium that are able to put this ambitious idea running forward. I thank you all for being present here, and we will be available to answer to all your questions. And we hope to, in the near future, to present with more detail some of the results that we are achieving and to share with all of you. Thank you so much.
Thank you, Bruno. Just a reminder for all the participants, you can enter your questions in the chat or also on the Q&A box, and we will answer them at the end of the presentation. Thanks again, Bruno. And now I'm introducing Elise Daniel for the THOR project.
Yes, good morning, everybody.
Morning.
I hope you can see my screen.
Yes.
It's a little bit long.
It's taking a little bit.
Okay, is it good, or do you see?
Not yet, but I think it will be good.
Do you see one slide, or do you see it?
No, perfect.
Oh.
Yeah.
Yes, okay. Okay, so good morning, everybody. My name is Elise Daniel. I'm working in CINEA in France, and I'm coordinator of THOR project. So THOR project aims to develop an innovative methodology for battery testing. So as already explained by all the previous speakers, we are facing the issue that battery physical tests are really expensive with high environmental impact. Actually, we need to make a lot of tests for cell, module, and pack validation. So at each step of the battery development, we need to make a lot of tests. And we also need to make some physical tests to develop the models. If we want to run simulation, we need also to calibrate the model by making some physical tests to get the real data of the different parameters for the models. All these physical tests are long, sometimes several months or several years, especially when we are investigating the aging mechanism. Most of them are destructive, and so it consumes a lot of samples. Those tests are generally complex because batteries are a very specific object which require specific facilities, and we can also face some safety issues. So we really need to design the experiment very carefully. And finally, all these physical tests are generally not enough and not enough representative to get the precise prediction of all the behavior of the battery. So in terms of performance, aging, and safety. So in THOR project, which started in June 23, we are working with 9 European partners. So with RTO, also industrial partners, working on cell, module, pack, and also on usage of this battery. And finally, we have also some company developing digital twin. And we have also research center. So the aim of the project is, as for the other project, to decrease the number of physical tests to be more effective, more efficient. And by developing a virtual tool, so a digital twin that will simulate the battery behavior. And in the project, we target the mobility and stationary application, and we focus on the common battery chemistry, which are NMC graphite and LFP graphite. The expected impact at the end of the project, so with the digital twin, we aim to increase the competitivity of the European battery industry, for sure, decrease the time to market by replacing this long and complex physical test during all the battery development. We aim to reduce the time and cost for the battery development by at least 20 to 30%. And also, thanks to these new tools, we aim to improve the battery design for better reliability, longer lifetime, and better safety. So finally, we aim also to reduce the investment needed for the testing of battery system. So the outcome with the result of the project, we should be able to predict the best set of parameters to design a better battery if we want. If we know precisely what will be the final usage, we can make some virtual testing and predict the best set of parameters to design the battery. And we will be able to perform more virtual testing, and that will become more common. So this is something which will be possible if we develop a virtual tool which is quite easy to use. And finally, it has also been explained a little bit previously. We need to harmonize, to standardize the data format with ontology, and to get this harmonization of the data to be sure that it can be reused by machine, by computer, if we want to be more efficient. So the specific objective of the THOR project, so we have actually 5 objectives. First, we want to develop a high predictive model for the performance of the battery. We want to develop also a physics-based model for the aging behavior at cell, module, and pack level at each time. For safety, it's the same. We want to develop a precise physics-based 2D model. And then with this 3 physics-based model, we go through the 4th objective, which is to construct the digital twin, where here we will use some reduced order model. And finally, we want to design more smart design of experiment and methodology to help building such digital twin. So if we go deep further in the objectives and we see the KPI which are associated to this objective, actually we want to be really precise with the different models. So for instance, for the performance model, we want to be at least at 95% precision on the capacity prediction, for instance. We want to divide by 2 the number of parameters needed to develop the model, and decrease by 2 also the time to calibrate the model for a new chemistry. We don't want to redo and to spend a lot of time if as soon as we want to change something in the battery. We want to have this adaptation which is quite fast. For the aging parameter, it's the same. We want to be precise on the prediction of the capacity, voltage, all the specificity of the battery. We want to decrease the number of channel months which are required to make the test, the physical test. So here we want to decrease by 3. And once again, we want a quick optimization and validation of the model for an optimized chemistry or a new battery design. And for the safety, once again, it's the same. We want to be precise here on the heat released by the cell, module, or pack level. Also on the amount of gas that will be released by the system. We want to decrease the number of physical parameters and physical tests that are needed to develop the model to only 5 abuse tests at cell level and 2 at module level. And as previously explained for the other model, we want a quick adaptation of the model for other chemistry and geometry. For the digital twin, in that case, we want an amalgamation of the performance, aging, and safety prediction. So we want that all these three models can work together. We want to access the result in less than 1 second instead of hours for the high fidelity models. And we want also to have a graphical user interface which is user-friendly. Because if it's something which is very too complicated to be used, the end user cannot use that, and it will be useless. Finally, what we expect by designing some smart design of experiment, actually it is developing a user-friendly methodology, once again, using simple tools like lab cells, lab facilities, with short time for the performance model parameterization. Same for the aging campaign. We want to focus on some specific parameters, and so making very specific tests only to get these parameters. And we want, for the safety part, developing an experimental method which is able to determine this total heat emission at the cell level, and which is reliable for the model at module and pack levels, to avoid making all the tests at all the scale. So in the end, at the end of the project, we should have these 3 physics-based models, which are very precise and which can give the behavior of the battery at different scale, cell, module, and pack. We should be able to provide some safety and risk reduction by providing a better understanding of the mechanism, the physical mechanism inside the battery, and provide also a better energy management. And so we will be able, for instance, to optimize a recharge profile or something like that. So where we are, and how do we work? So first, we have started with the specification and prototyping. So here, our industrial partners are working a lot on that. So it is still on progress. And we have also started the development of the physics-based model for performance, aging, and safety. So this is the task under progress. Then at the end of the year, we will start the development of the digital twin with a reduced order model. And finally, we will validate and demonstrate that the digital twin can be used for different user case with our industrial partners. So these are some details about the samples and chemistry that we are studying in the project. So we are working on NMC graphite prototype cell made by Varta. So those cells have been specified and designed especially to design and to develop the best models. So they are not the best performing cell, but they are very representative of the market, and they are designed for the model development. And we are also looking at the LFP graphite cells. Then we have some module and pack, which are assembled by flash battery. And once again, those module and pack design has been defined to help the model development. So this is under progress. Regarding the physical test, as for the other project, we are making some performance, aging test, and abuse testing to get mainly the input parameter for the model development. So we are doing it at the cell module and pack level, and we will do also a few post-mortem analysis, destructive analysis to confirm the hypothesis on the mechanism. And we are also developing some numerical tools. So we have this Stellar database, which is used in the project, where we are gathering the harmonized data and metadata on all the samples and all the test results. We are also trying to have a common format using the JSON format. So this is this goal to standardize the data format. We are developing these P2D Newman models for performance, aging, and also we have this model for the thermal runaway prediction. So these are the work in progress, and in next year, we should work on the reduced order model, and finally the development of the graphical user interface for the digital twin. So thank you for your attention. And if you have any question, don't hesitate to put in the chat or in the Q&A session. Thank you.
Thank you, Lisa. We have already one question, but we'll address it at the end of the presentation.
Okay.
And now Lorenzo Bersi for AccCellBaT project. Welcome, Lorenzo.
Yes. Hello. Can you hear me?
Not good. I think.
Now?
Now, yeah, better.
Okay. Okay, just let me present the screen. So, yes, can you see that? Okay,
Yes.
just a note. I am Lorenzo Berzi, yes, but University of Florence is not the coordinator of AccCellBaT, just please note. It is AVL. Of course, we have the role to present this part. So let's see the project overview. We are a group which comprehends from, as usual, some academic partner and some industrial partner. Let's say that we have industrial case studies which will be shown later, and overall let's say that most of the project time has passed, so we are running until March 2026. Let's start describing our case studies. This is the approach we selected when writing the project. We wanted to reduce development time, which is a target comparable to the one of our colleagues in the other projects. And we set as a reference case study the automotive use case. In fact, we have the Stellantis and the Fiat Research Center on board, and the use case of the stationary battery, and we have VARTA storage and VARTA innovation on board. Let's say, again, our target, which is similar to the other project, is to reduce the development time of approximately 30% or more. And I would say we also would like to define which testing methodology can be used for different sectors, which have different needs, of course. And also to provide some data and to automate the battery verification and automation project. Here I can show you the project acceleration strategy. But again, what is our motivation, let's say? We know that even if we have many opportunities today to run simulation models for battery, at the same time, we need so much time to get the data to validate these models. And also we have a relevant issue sometimes in coordinating the model input and output with different platforms. What we want to do in AccCellBaT is to improve the development process with simulation models which are using latest cell measurement methodologies, and also to create a data platform. I will show that later, with where all the information are put in relation with each other. And this is, I would say, a point of strength of the project. And also to validation, to push validation activities in a continuous manner. Here we have the main role of the partner in an approximate manner. A few examples. This is a model development process which starts from a special test. In practice, we are studying not only the cell degradation and material degradation models in the physical manner, but also with hybrid methods using numerical manner. This part, which is managed by University of Bayreuth and is using the VARTA innovation cells, is, I would say, mostly concluded. And the target again is to short the testing time through model training in an efficient manner, starting from, again, measurement. This part, and this is us, University of Florence, which are managing that. We are defining multi-domain models. For example, we are coordinating the mechanical model creation, which is very useful for the virtual crash test execution. Here we have an example with the cell. And the thermal model, which is relevant, of course, to study the modules and the battery as a whole, so a system, not only a group of cells. And of course, we have some electrical model, and we chose to use a functional mockup interface to deal with different platforms. So this is how we are organizing the model. One part which is very relevant, in my opinion, in AccCellBaT, since we want to study the battery from an industrial point of view, so sometimes with a relevant TRL level, we are also dealing with the wiring hardness modeling, because it's part of the battery as well as the cells, the spacers and other subcomponents. In particular, we have some fatigue methods and fatigues tests which lead to the creation of damage model. And these are needed to understand if there are some issues, especially for the automotive use case, during the life of the product. In practice, the damage model is derived from both from simulation models and the measurement data. If we look at the advanced measurement method, we have some applications, especially developed by the Collège de France, where we have the fiberglass sensor inserted into the special cell under study, and we have some pressure sensor again integrated in the cells. And the target of this part is to study new silicon layers which are used for the cathode, and to characterize in detail what's happening inside the cell in order to provide model creation in a short time using this special applications technologies. So this is how to deal with new cell technology. We also have, and this after we have been talking about these methods, these measurement, these models, there is the linked data management method, which is part of the AccCellBaT strategy. It's presented in the form of a website where all the partners can upload the data, and of course they can be collected and defined through some certain metadata. What we can do at the end of this process is that we can put in relation with a simple icon system where the model have been defined, which people are responsible for the data related to the model, and which data can be used for this system. Let me show you a very simple example. I prepared that. If we look for a very simple keyword, which is automotive, of course, we can look at all the items which are related to automotive, and we can see a knowledge graph. You can see some people which are involved in the preparation of this model. We can see the project related to the automotive battery, the system model connected to the project, and then many information which have the different data format, for example, or different use. For example, we have a list of failure mode, which is very relevant for the AccCellBaT case study and for the relation between cells and wiring harness. And we have some methodology tests which are connected to the project. So this is our response on how to deal with a very large amount of data. Of course, this website, I don't know how to call that, this data management platform is under development and not all the elements have been defined, but we are at a good test phase. So we have a very relevant part which is related to the development process and validation process. We said we want to reduce by 30% the development time. So it all starts with the requirement and the verification and validation demands. So what is needed to design a battery and to verify a battery. And then we have some methods which are applied according to the demands. And after that, we have a validation concept, let's say, which is done sometimes in parallel, sometimes in series with CIA, I mean, model systems, computer-aided engineering in general, and then some specific durability test or any kind of test at system or at cell or at vehicle or platform level. Of course, we need to calculate the specific test conditions and the criteria for verification of the models. At the same time, to calculate the damage related to the durability test, and in case to evaluate and optimize the system in order to get as output these parameters which are typical of industrial application at the high TRL level. Let's say that when we put all of this in relation, we have to make some frequent updates of the requirement and to update the output consequentially. But this is a response to the industrial case study. A very relevant part, of course, is to verify which systems, which contributions, which elements contributed to the failure mode of the automotive stationary battery, because this is the final target to obtain something which behaves as planned. And in the end, we put in relation this failure mode with the elements we have. How to measure the project success? We defined various key performance indicators, but in the end, the most relevant are these K simulation, K test, K automation, degree of automation, which are those who contribute to the so-called reduction of 30% in development time. Just let me highlight that not a single intervention can provide a single reduction of 30%, but our effort is to work within the various work package, reducing development time, and to make a cumulated reduction of 30%. The methodology to calculate the simulation, testing, and degree of automation efficiency is based on a similar approach for the three phases. The first one is the fulfillment of the product requirement assessment, then the maturity of a certain method, and the third one is the improvement in percentage that we associate with the activity. The product of the three provides us the key performance indicators. We discussed much on how to assess the reduction, and this is our best estimation for that. If we look at the status, let's say we have identified the main damage drivers. We say it's very relevant for our case studies, and this is almost accomplished. Of course, we have a battery system testing methodology, which is still under preparation, and it is the part where we hope to validate our 30% test time reduction. And in the end, I think this is a relevant contribution, at least for the partners of AccCellBaT, this framework to associate the data, which are very different because we have models generated in ANSYS, in LS-DYNA, in MATLAB, Simulink, Modelica, and so on, is part of the strategy to reduce the battery preparation, and also to cross-link all the information generated by battery development process. Just as a reminder, this is our contact, and of course you can contact us directly or through the TwinBATT consortium. Thank you.
Thank you so much, Lorenzo. Again, we will share all these presentation slides and the video. Now we can go for the questions and answers part. We have actually 2 questions for all the project coordinators. So I will start with the first one. How do you envision standardizing or aligning your different digital twin approaches and testing protocols across the 4 projects to support interoperability and future collaboration within the European battery testing ecosystem? I think I can also write this in the chat.
Yes. Who should need the response to this?
Yeah. Who wants to answer this? Or maybe 2 speakers.
I think I can tell at least one part that is ongoing topic for the cluster is we said in the beginning, we are a newborn cluster, and we are still trying to understand how we are going to can I say, it's not to collaborate, but how we are going to interoperate between us, because we met a few months ago. We are still trying to understand where our works are going, but we are also trying to understand where are the boundaries for each of our projects without interfering with IP. We cannot interfere in the intellectual property that it's been developed in each one of the projects, and we need to understand where we can start developing those type of things. One thing is sure, and the European Commission is trying to push these with clusters, is the interoperability of our data, or at least that we must share in some point of our journeys, that we are now reaching very fast the end. We are already seeing the end of the tunnel, the light in the end of the tunnel for our projects, but we are trying to understand where we can cooperate. And even if it's nothing like it was asked, standardization, because we are tackling at the same time, it looks to similar things, but in other points we are doing a lot of different things. But at least a common white paper, common guidelines, a common base, it will be something that we are aiming to try to do in the end. But we are still very young, and we are still trying to understand where we are going with the cluster. This is our first event. We are putting ourselves to the world, and we hope that from this point on we will keep pushing things, and we will probably be appearing in some conferences as a TwinBATT cluster, and this will be for sure a topic, and we will try to address. I don't know if any of my colleagues also want to say something about this.
Yes, in general, I agree with your view. It's not a long time we started coordinating as a cluster, I would say. Also from the presentation of today, I've seen that there is a certain accordance regarding the target to be achieved, and also the problems which arise during project execution. Let me say something which is putting all of us at the same level is the adoption of suitable standard for example, for cell testing in the electrical, in the mechanical way. Even if, let's say, due to the technology evolution, these standards are continuously evolving. And in some cases, the standards don't simply exist. So, for example, if you want to assess in simulation manner how the battery thermal runaway will happen, in many cases you have to deal with let's say industrial standard internal to the partners, but we have a common basics from which we can start, and this is defined by the standard, in my opinion. Regarding model generation, well, even if I'm not so expert as other colleagues, I can see it from different activities, from the different European projects, that we have many approaches to define the models, and sometimes you use very good models which are somehow dispersed across the various institutes, across the various industries. But the more you can divulgate that, the more it is probable that they will be used in the future. And how do you disseminate your models? With scientific literature, so it's a very good idea to define a white paper, for example, for the cluster, and also with consolidated, I can say, simulation models in a shared platform. So, for example, to create, Modelica open source pack would be very, very useful for the future of the cluster. Just to say an example, I was seeing that in THOR, if I was not wrong, they were talking about an open source pack. That's it.
Thank you both. I think, Lorenzo, we have a question for you.
Mm-hmm.
Because this was for the last presentation. How to check the quality of the data and what are the metrics?
That's a very good question. I suppose we are referring the quality of the test data for the cells, and which are the metrics. First of all, regarding the comparison, when you introduce a new method, and honestly, the colleagues from Collège de France are much more expert than me in this special measurement method, you make a comparison with, let's say, the methods which are used up to that moment. So we have a continuous parallel execution of testing, let's say innovative models, innovative systems, innovative testing systems, compared with, let's say, regular one, or with standardized procedures. So that's how we proceed, ensuring that the data are coherent with known methods. Regarding the metrics, this is a very good question, because at the beginning of the project, we were discussing which metrics do we use for the cell, for the module, for the battery, and plenty of metrics can be used, and each partner is giving a different meaning to the word metrics depending on its background. So industrial partner define metrics mainly in terms of, let's say, performance for their application, where a different standard is applied. While research institute tend to give the word to metrics to, let's say, physical performance. What we wanted to do was to aggregate these metrics, and that's why we have this data platform for which I did a very short demonstration, to compare, to see all of them in the same manner in order to find which are the most relevant. And regarding the matrix of the matrix, so how we reduce the time needed to assess a certain matrix, which is a composite matrix, let me say, we had a lot of discussion. So the method we proposed, which is based on the achievement, which is based on the assessment reduction, and which is based on the precision of the results, is one of the many methods possible. So we will do our best to demonstrate that this is a useful method. I hope this responds to the question.
Thank you. We have another one for all of the speakers. I will also put it in the chat. And it says, given your shared emphasis on digitalization, and virtualization, are there plans to create a shared open access platform or repository? I think Bruno said something about this at the beginning, but
yeah, I can respond for AccCellBaT. For the moment, the platform is only accessible to the participants of the project, and some, I would say, reserved data are inserted on that. So I'm not sure that it will be used to the general public soon. I guess that we will make some demonstration with a limited subset, which will be shared at the end of the project. This is my prevision.
It's also the same for our side. I think we have some part of the information that can be shared, but the main core of the digital twin, it will be something that it's considered sensitive, and it will not be, at least for now, public available. But the idea probably it's like Lorenzo said, we are also going to have a demonstrator. It will be, at that time, it will be open to the public, and after that, it's something that we need to evaluate how it goes further regarding IP and all of those approaches. So it's also our take.
thank you.
I could just add
yeah.
on behalf of DigiBatt, as Lorenzo and Bruno said, a lot of the stuff there is not going to be shared immediately. But the stuff we're working on in DigiBatt is quite a lot of things are based on the open source software that we have. So I think probably as a cluster, we won't have a shared platform, but for the individual projects, you will be able to access some things. Yeah, so there is opportunity to access things. And also because we have this open source idea, and other projects as well are using or interested in open source data and open source models, then there is opportunity for us to work together on that and share things within the cluster as well, which can be available for other people.
Yeah, and for THOR, it's the same also as the other. We have this repository, which is called Stellar, which is used internally by all the partners of the project. Some of the data set for sure will be made public in the end. So that's why also we were working with very standard chemistry, with also some commercial cells. And the idea is really to disseminate as much as possible on the data we get, how we get it also. And this is a plan in the end of the project, but yeah, it is something we have to discuss with the cluster, how to deliver it, all these data set in a common way.
Thank you. We have one question by Florian, but I think it's about the same topic. So is there a plan at the end of all these projects to merge the created project internal standards regarding data transferability for a standard, including all identified needs and metadata?
May I respond that,
Yes.
as Bruno said, it's not a long time. We started interfacing the various projects. So since this is the second time we see a similar request, we should consider this this thing. Yes, but it is the matter of the last year of these projects. That's my opinion.
Yeah, I would agree with that. We haven't planned very much so far, but this is the sort of kickoff to try and get us thinking and planning. So if other people have ideas and suggestions of things they would like us to do as a cluster, then we're very open to suggestions and ideas, input.
Yeah, to reinforce what Francesca and Lorenzo says, we are still brainstorming in a lot of things that we have to do. We just kick off as dissemination activities, but we need to push and to try to think. And if it's something that it matters to everyone, probably we need to push, like Lorenzo said, this forward and to try to find a solution. And now we can work on this without interfering with the scope of the projects, but at the same time to be useful, because that's the goal of the projects, to be useful to Europe also. So I think it's something that we need to tackle in our next cluster meeting and to try to understand how we are going to do this. But it's a good question, and thank you so much.
Thank you, Florian. It's an interesting topic. And yeah, you can stay tuned for the upcoming TwinBATT activities and webinars or workshops.
I can see there is another question specific for AccCellBaT and to the wiring harness verification. How do you ensure accuracy of the damage model across temperature and vibration conditions, especially consider the complexities of real-world automotive use case? In practice, we have, I would say, not me personally, but our colleagues in Gebauer and Grill, they have a consolidated method which are sharing with us, and it starts with conventional mechanical modeling, of course, with special elements which are appropriate for wiring harness and for connectors, because also connectors are a critical part. So it's something like a response vibration model, force vibration response model. This is the starting point. Regarding the boundary condition, as we said, we try to put all together the relevant standards. So, for example, a driving cycle combined with surface where the vehicle is running. As far as I can see from the research institute, it seems that many that the industrial partners, each one has his specific methods. For example, in Stellantis, they have many a research center for batteries in Turin, and they provide certain thermal cycles for a long time. It's almost 2 years test plan. How to deal with time reduction in this? We don't know exactly at the moment because it has to be defined at the end of the project. But the idea is to merge all the relevant information and to provide a statistically valid solicitation plan, which will be, of course, accelerated enough to contain the time of the development. But let's say the 3 steps are boundary condition definition with suitable standard and partner know-how, modeling with mechanical elements, for example, like finite elements as main part, and then validation of the system with proper set and subset. Set is the full battery which is tested. Subset is a test bench, let's say, with proper excitation system and support system which is emulating the real part. So it's a difficult task to summarize it, and you have to deal with many data.
Thank you, Lorenzo. Bruno, we have a question for fastest.
Yes, I will try to answer. I'm not the most technical guy in this, but I will try to tackle the question about, if you want, I can read it.
Yep.
If we can elaborate on how smart design of experiments algorithms in fastest adapt in real time to test results, and how this might reduce the number of physical prototypes needed. How we are trying to tackle this situation, we define a DOE that takes in account the sequence of tests that is putting together by the user input. Then we try to understand if these tests can be virtualized. If they cannot be virtualized from the top, we will need to go to the physical test bench and to do the request for this to happen. But if it is already something that we already have virtualized and that we already have a suitable model available, this can push a lot of steps and can push things forward. And it will pass several questions. And in that point, we reach the point that we can try to understand if this can be optimized. We have a lot of things that it's a lot of data that it's been put that we are running. Also, like I said in the presentation, we are trying to cover the 3 use cases. So we have information about these use cases and the most common base. And with this in account, we try to understand how we can perform and how we can speed up with also together with the models that we are already creating with reduced order models, the data-driven models. And at this time, we try to push and to speed up this situation. I don't know totally how this, because to be honest, I can answer to you in a more concrete way to the person that put this question, how we can answer this in a more proper way about the physical prototypes needed. But since we are running and since we have, I think we will only need to run in physical test benches a very small number of cases. For you to have an idea, I forgot to tell in the presentation, we are running all these models and all these cyclings for generation 3B and to generation 4, to solid state and to LFP, to the most common batteries that are. So we try to cover a lot of things at the same time, and we hope that with this approach, we can try to speed up. But to be honest, to give a proper answer, I will address with my colleagues, and then I will return. If you want, you can leave the email or send an email directly to me, and we will answer you with all the with a proper answer, not mine that I think I tried to address. I don't know if it was the ideal one and if I answered totally the question, but I will be available to answer this with my colleagues that are the experts on this part.
Thank you, Bruno. We will share, of course, the contact information for projects. This was the last question, and we're 10 minutes ahead of time. So I think I will close. Thank you so much for all the participants and for all the speakers. This week I will edit the video and send it by email, as well as the presentations, and you can find them on all the websites. So thank you so much. This was the first activity of the TwinBATT cluster, and I hope to see you in the upcoming ones. Thank you.
Thank you.
Thanks.
Thank
Bye.
you so much.
Wish
Bye.
you all a
Very much
good day. Bye.
to all the people here. Thank you very much.